video, we worked through an example of a polynomial inequality. I've just written down the steps up here that will apply to both polynomial and rational inequalities. I've got a 5-step process written down here. Not super important to memorize the steps and think, what is step 3? But it is important to be systematic about things. I also just point out that the book lists their own version of the 5-step process on page 323. Our steps are essentially the same. I've reversed the order of steps 3 and 4 because I like to do what I call step 3 before I do what I call step 4, but it actually doesn't matter. You can do those steps. You can interchange the order of those steps. Okay. I would encourage you to just take a look at the book steps just because I phrase things a little bit differently than they have. I've put things into the words that make the most sense to me. Sometimes reading the same process expressed 2 different ways helps you to figure out how you would phrase it so that it makes the most sense to you. Okay. So the very first thing is to get everything on the left side and be comparing it to 0 on the right. Now, last time we didn't have to do anything because we were given a problem in that form. But it's actually very, very important that we end up comparing things to 0. The reason is when you're comparing to 0, you're talking about bigger than 0 being positive and smaller than 0 being negative. And when you're talking about signs, if you know the signs of the individual factors, you know the signs of any products or quotients, once we start talking about rational functions, that you can build out of them. Whereas if you're comparing to 2, if I have 2 things that are smaller than 2, that doesn't necessarily mean that their product is going to be smaller than 2. So knowing how each individual factors compares to a non-zero number is not helpful in figuring out how their product or quotient will be. That only works if you're comparing to 0, because comparing to 0 is talking about the signs of things. So that's going to be very important, and not all problems are going to come to you in that form. So you may have to manipulate, and I just noted here, that means you're going to have some function, and it's either going to be less than 0, less than or equal to 0, bigger than 0, or greater than or equal to 0. Okay, once you've done that, you want to completely factor the left-hand side. So you want to get it so that everything on the left is connected to every other part on the left by multiplication or division if you've got a rational function. Because if I'm combining things with addition and subtraction, if I have a positive and a negative and I'm adding them, I don't know what the result is unless I know how big each piece is. But if I have a positive and a negative and I'm multiplying them or dividing them, I know the result is negative. So I want to get everything factored so that knowing the sign of each piece is enough to tell me about the sign of the whole thing. And once we've done that, we'll find the boundary points. Now the boundary points are just the x values that would either make the left-hand side equal 0 or make it undefined. Now as long as we're dealing with polynomials, they're always defined, so the boundary points are just what makes the polynomial equal to 0. But once we start working with rational inequalities, anything that would make the denominator 0 makes the rational expression undefined. Okay. So those will be our boundary points. Those are going to be the places where the expression that we have on the left could change sign. Okay. Corresponding to the fact that polynomials can only change signs at their zeros, and rational functions can only change signs at their zeros, or where there's an x-intercept. I guess we didn't use the word 0 for a rational function, but at the x-intercepts where we cross the axis potentially, or at places that are not in the domain. So if you had a vertical asymptote and the rational expression was undefined, sometimes it was positive on one side and negative on the other. So that's essentially what we're checking here. Okay. Then you decide whether or not to include the boundary points. I like to draw a picture on the number line as I'm going. So if I do include the points, I'll put a solid point. If I'm not including it, I'll put an open circle. That's just drawing a picture of my answer, which I'll ultimately give at the end. Use test numbers to determine the sign of the left-hand side by checking the sign of each factor and then seeing what we get. And again, the book reverses the order of these 2 steps. It doesn't matter whether you deal with the intervals or the endpoints first. Step 5 is just to write your answer. Now the textbook says to write your answer in either interval notation or set builder notation, but wherever it's possible, they always give the answer in interval notation. So I'm just going to say, let's just stick with interval notation, and we'll do that. That way, when you're checking your answers in the back of the book, you've given them in the same format that the authors have. Okay, so those are our steps. Again, not super important that you sit down and memorize, this is a 5-step process, I must know what step 3 is, but very important that you are systematic about doing this. So I'm going to have you folks try a problem. And again, I picked a number from the homework. So this is number 25 from the homework, and it is one of the assigned problems. It's a squared bigger than or equal to 3a. Now here the variable that they're using is a instead of x. Totally fine. When you draw a number line, instead of it being the x-axis, it's going to be the a-axis. But you can go through this same process. I will just point out that here, that's not 0. So you've got a little bit of work to do in that first step so that you're comparing something to 0 instead of comparing two expressions, neither one of which is constant at 0. So go ahead and try that problem, and then in the next video we'll work through it together.